This is a GRIDeoS about homogenization. Not all materials have properties that are listed in tables or in books. Materials like cellular materials, materials with complex structures, or composite materials, which are more common, they have some problems. They are difficult to predict in terms of behavior, leading us to the need of certain specific studies, like effective properties, to know exactly how the material behaves, the representative volumes, the representative portions of the material that can help us study its behavior, and even multi-scale procedures, which relate the overall structure with the material influence. So, where does all of that put us? What do we have to do? How can we study all these things? One of the main things here is we can use a simple problem. Let's just imagine that we have a structure, a given structure that you want to study, and it's made of a base material. You have a set of properties that are corresponding to that base material, so which is okay. You use those properties and you study the structure. You model the structure, you calculate its behavior. If you have different materials over that adds up to the same thing. So each region has its own material, you use its own properties, it's okay. So if you imagine that we have now the same structure but built from a material that has a tiny length scale, and you have to study the behavior of the whole structure. What do? You can use the strategy seen before, where you model the whole structure with the whole detail, and for each one of the regions, each one of the portions that you have, where you have a given material, you use its properties, and for the other ones the same thing, but that is fairly heavy. Is it possible for us to use a representative part of that material to model the whole structure? That would be ideal, so that you could use the whole structure as if it were made from a homogeneous material, but you used some kind of heterogeneous properties to model it. How can we do that? How can we get those properties? How can we use them? That brings us to the concept of homogenization. In homogenization, what you do is you take heterogeneous media and you get a representative part of the detail of the medium, of the material, and you study its properties, so that you can use that representative part and its properties to model the material behavior, and then you substitute the detailed structure with all the material details for an approximate structure where you have a homogeneous material, which should simplify the model, the workings of the model. In practice, how does it work? Basically, what you do is you take the overall structure as if it were made of a single, and basically you use the material properties that you take from that representative part of the material on the homogeneous or the substituted homogeneous structure. With that, you use the same set of material properties, or the same set of numerical properties that you would use with homogeneous material, but you take those properties from that representative part of the heterogeneous material, of the composite material. For this can come back and forth. You can use the material properties to calculate the behavior of the whole overall structure, but you can always do the inverse. It depends on the strategy you use, but you can also take the behavior of the overall structure that's behaving as if it were homogeneous. You can take some kind of variable and put it back into the micro scale, back into the material, so that you can see what does that given variable represent over the detail of the micro scale. That is called localization, which is the inverse procedure relative to homogenization. So basically what you have to do is to study the material properties, the local material properties, using the properties of each one of the components, the material components that make up that composite material. But if you don't use a composite, you use some kind of foam, cellular material like metal foams, for instance, you can do exactly the same thing. You can also have structures with different composite materials or different complex materials, on different regions. Use these kinds of methodologies to study the material in isolation so that you can have a set of material properties that can later be used to study the material or to be then used in a structure as substitution properties, as effective properties. So let's just think of an example just to finalize. I don't know, a competition automobile, and you take the example of the struts, the wing struts, which you wish to be very light, but at the same time very stiff. You can study different materials. You take some kind of representation of the materials. You choose what kind of unit cell, what kind of representative volume you're going to use. There are many alternatives. And then you study its properties so that you can use those properties on the structure, on the strut in this case, without using all the detail, all the tiny infinite details of. And then you study the material. You can do lots of studies of the material to have its overall behavior in different directions with different representative cells. Try out different materials so that you can get an overall glimpse of the overall behavior of the structure, how it will it work, how good an approximation you have to whatever set of properties you wish, before you go into testing and to real fabrication of the overall component. Thank you very much.